Okay, Bismillahirrahmanirrahim. Now moving on with paper 2 with unit 13. In unit 13, we'll be looking more at the data types and identifiers and the different manipulations that take place with the data types, following with what an array is, what bubble sort is, then two-dimensional arrays, and followed by your file handling using your algorithms, how file access is being used in your paper 2 attempts, right? Now, let's begin with your, first of all, by understanding primitive data types. Primitive data types are basically data types that come equipped with most programming languages. So, for example, integer, if you want to hold data that is of whole numbers only, you will use an integer data type. And this is an example of integer data. Real will have only fractional part as well. So 3.45 is an example of real. Okay, by the way, both integer and real are signed values, so we can have negative positive both values. But the interesting part is that they have to include a fractional part. If you're dealing with Boolean data, that means that you can have either a true or false value. If you're looking at character data, they can have only these letters of length one. So A, C, a 4, even though it looks like a digit, but if it's enclosed in these inverted commas, it's a character. No arithmetic operation is allowed with 4. If you want arithmetic operations, then you stick with integers. 4 is just, it's just for the character 4. It will be considered for its ASCII value. So anyway, these are my primitive basic data types that most languages come equipped with. So apart from that, we have, say, for example, date as well. Most languages, unlike Python, most languages do have a date time type. So if you are saving some information about dates or times, then you will use the date keyword, the date data type. Even for time, you will use for date data type. Python, on the other hand, does not have a by default date data type, but you can hold date data by importing a date library and saving date information according to that. It works. You can do it, but by default, talk about primitive data types. It's not a primitive data type. It's not by default. It's basic data type. Okay, apart from that, we can create further variations in these basic data types and say, for example, a string. Now, what a string is basically is a sequence of characters. So if I want to write 12 as an integer, you see I don't write double quotes here. But if I write 1 and 2, as you can see here, these are two characters. And the two characters can be combined to form a string. Whenever you're mentioning string, you'll have to use a double quotes, single quotes of characters, and double strings, the double quotes are for strings. And similarly, if you want to assign an empty string to a particular value, it means nothing. So if you just want to, placeholder value for a string type of variable, you can use an empty string, and it looks something like this. Double quotes only with no data in between. Apart from that, you can mention date as a string type with double quotes, but then you can forget about any arithmetic operations whatsoever. So let's just say you want to calculate 3 days from now, calculate 5 days before this, you want to add a day, add a month. You won't be able to do that if this date was saved as a string, because no arithmetic operation. And for specifically these type of operations, we need to have a separate date type. Now, after that, we'll have something known as a record data type. If, say, for example, you are unable to solve a problem with your primitive data types as well as your further data types, you can create a user-defined type. So user, by user I mean the programmer. User can choose to create a data type of their own. Now, the data type we're looking at right now is the record data type. Record is known as a composite data type. Now, composite data type means that it is combined of two or more other reference to other data types. Now, these other data types can be your basic primitive data types, or they can themselves be your records as well. So that doesn't mean that you can't use a record within a record. That's, you can do that. But for example, this is what a record data type declaration looks like. By the way, you'll have to declare on here because it doesn't exist yet. Is you'll create it only for your problem, so you have to declare it on your own. So how do we declare a record data type? Say, for example, I want to create a record data type of the type student. So how do we do that? We write type followed by the name of the data type I want to create, that student, and I will enclose the different fields and their data types that it's supposed to hold. So a student record data type will have 1, 2, 3, 4, 5 5 different fields. Each field will be name will be of type string, date of birth of type date, height real, siblings teacher, and full-time student Boolean. So each variable which is declared of type student will have these 5 fields in it of these specific data types. Now, if you're done declaring your record data type, this is how you go about using it. You want to declare a variable of this type. So you just created a type, you want to use it. How do we use it? Declare this is my variable type, this is my identifier. This symbol here means of type student of type student. Now if I want to access individual fields of student one, I can use the dot notation. So I want to access the student one's name, so student one dot name, and I want to assign this Adam to the name of student one dot name. This is how it's done. I want to assign this date to student one's dot date of birth, student one dot date DOB, assign this date, student one dot height, assigned with 1.5 cents, student one dot sibling, assigned with 2, so on and so forth. You can also output a particular field in the record using, so if you can take inputs, you can also do outputs like print. Yeah, output, you can use output keyword as well. Output student one dot name, like so. Similarly, if you talk about arrays, now basically what an array is a data structure, and it's basically a collection of the same type of data that is related in some way. So if you, for example, you want to save the marks of a student in a class, that's the relation of every student in the same class, and you want to save only the marks. So all students will have marks of the same data type. So this is a very good example of where an array should be used. Why would I want to choose an array? Well, say if I have to say, for example, I have 10 students in a class, I want to save 10 marks to students. I can choose that by assigning 10 different variables, which is difficult. You have to think of 10 identifiers. You have to make 10 separate declarations, 10 separate assignments. That's not an easy thing to do. That leads to greater codes and possible greater mistakes as well. So it's not a good approach. What we can do is that we can assign these collection of data and give it just one identifier. That would be the name of my array, my single one identifier. Based on that one identifier, I'll be accessing all students, all information. This is the benefit of using but array has its limitations. You can't add data in between it. You can't delete from anywhere in between it. For that, we have to make use of special types of data structures. But our basic data structure is an array. It's a collection of the same type of data that is related in somehow. And if they are related somehow, we can assign all, we can use all of those different data values with just one identifier. Arrays can be both one-dimensional and two-dimensional. We'll be looking at both in a bit. And individual elements in an array are accessed through their index positions. We'll be looking in that a bit as well. So first of all, you have to declare an array. For declaring a declaration of the array in pseudocodes, you'll have to use the declare keyword followed by the name of the array you want to choose, of type array. Where does the first index position start? Where does it end? So lower bound to upper bound. And then finally, you'll have to mention the data type of the array. One thing to note here, that all related data will have to have the same data type. So array, whether it's one-dimensional or two-dimensional, it will have to have the same data type. So you have to declare your data type here. So for example, I've got max marks. This is my array's name, of type array, size, index position 1 to 8, of type integer. Now basically we have created an array called marks of size 8 because first index position is 1, last is 8. Similarly, we have created an array heights of size 0 to 7. This is also 8. But in this particular example, we are starting index position from 0 onwards, and that's also fine. In fact, most programming languages use index position 0. Pseudocode is not, there's no hard first rule. If you want to use 1, you can use 1. If you want to use 0, use 0. But for your solving the paper, you have to make sure what the question is asking. If the question is asking 0 position, you'll have to follow 0 position. Okay, then what do? I want to access a specific element in my array. So that's where indexing comes in. So for example, I want to access the 7th position, whatever is in 7th position. of my marks array, this is how I do it. Marks index position 7. In this particular example, you can see that I'm assigning the value 50 to index position 7. So my seventh mark of that class becomes 50. Similarly, if I want to print a value, I can also do that. For example, my heights array begins with index position 0, and printing the contents of heights array at index position 0 means that I'm printing the first elements that's stored in heights array. So same thing, when you work out the indexing, you can access, you can treat it just like as any other variable. You can also create arrays of record data types as mentioned before. So for example, I created an array non-students of size 30, index position 130 of type student. So that means that each index position of students, there is a record that holds all of these fields, all of these fields. And how do we access individual fields of a record in my array? Again, indexing comes here, but this time I'll have to use the dot notation for each index. So for example, I want to access the fifth student, students index position 5, and I want to access the name only, dot name. So I'm assigning the name Ahmed to students in the fifth position dot name. Similarly, if I want to do this, print students at the sixth position, the sixth record in students array, and only the height, so dot height. So I'll print the height field of the sixth record in the students field. So this is how arrays are used in one-dimensional arrays for both your primitive data types as well as your record data types. Now, you may be required to carry out different operations in an array. One of them is assigning values to an array. Then obviously at some point you will be required to search elements in an array. When you want to assign elements to an array, it's best to do it through a loop, because otherwise you'll have to write separate lines for each assignment. So what, for example, in this code, we can see that my counter runs, I got a for loop here, counter runs from 0 to 6. And I also have an array that starts from index position 0 to 6. So I simply do is, I will run this code 7 times, 0 to 6, 7 times. And in each iteration, I'm simply taking the input and I'm placing it at the counter position at the index position, which is highlighted by the count value of that particular iteration. So for example, if my count is 0 at that time, I'm taking an input and assigning that to my array, my list index position 0. If my count becomes 1, I assign it to my list index position 1, so on and so forth. So after this entire array is run, I have input 7, entire loop is run. I have input 7 values like so: 25, 34, 98, 7, 41, 19, 5. And if I want to print individual elements, same thing. For count 0 to 6, print my list, the elements at that index position highlighted by the counter of that iteration, and move to the next place. There should be an end for here. Anyway, so print out all elements same using the for loop. So what that means is that my indexing value here doesn't actually have to be a value as we've seen over here. It could be a variable, and it could be something that changes its contents, like it's happening over here. So let's look at the first operation in using an arrays and the searching for some value in an array. Okay, when your array is in random order, there is this algorithm known as linear search, and that is the only way you can do it if your array is stored in random order. Now, by random order, it means that all elements in your array are unordered, random data. So just like this, random data. So if my data stored in array is random, out of order, then linear search is the only way that I can use to find a particular element. Linear search means that I simply access each index position and see if that is the value I'm looking for. If it's not, I move on. See if that's my value I'm looking for. Move on, move on, move on until I find the value or I reach the end of my array. So brute force approach, pretty simple, but it takes a long time. And if the array becomes longer, it will take even longer. So that's a problem with linear search, but if your data is stored in random way, there is no other way. If it's sorted in ascending or descending order, then I may have a simpler, more faster algorithm known as binary search. We'll be discussing that in paper 4. But right now, linear search is the only way to go. Now, this linear search looks like this. My max index 6 shows the last position in of my array. So this array is of size 0 to 6, so 7 elements, and my last max index value is 6. So that points out the last value. I will take an input from the user. What are they looking for in my array? Whatever they are looking for, I will take them, take an input from the user and place it in this variable. I have yet not found it, so I will set my found flag. Any Boolean variable is known as a flag. I'll send my found flag as false, and I will start searching at index position 0. So while my index is less than equal to max index, and my found flag is equal to false. So this is a complex condition, and this is a while loop, so thereby it's a precondition. So if this condition is true, I will enter the loop. If it's not true, I will exit. I will exit this loop because of this being a complex condition. I may have to exit loop because either one of these conditions becomes false. So I have my index is not yet now lesser than or equal to the max index. That means I've exceeded my max index position. It has become false. Or it could also be possible my found is no longer false. It is now true, which means that I found the element I'm looking for. Because if it's this part of my condition will become false and I will exit it. So if this becomes false or this becomes false, I will exit the loop. Now, if I exit the loop because of this becoming false, that means I did not find the element. If I exit loop because of this becoming false, that means I found the element. So this is only one of two states that can take place. So if I didn't have not either reached the end of the array or I have not yet found the element, I will simply keep on going. So what am I doing inside the loop? I will access my index position that I am right now in my array and see if that element in that index position is the same as the element I'm looking for. If it is, set found to true and come outside and increment the index. So if I have found it and my found has become true, the next time I run around checking, I will have to check if this condition is true still. No, it's not true because my found, it has to be false. It is now true. I will exit the loop. No need to run it again. But if this is not true, it means I will keep on going. So you notice that I'm incrementing the index after the if block. This is gonna matter in a bit. Anyway, so let's just say I've exited the loop. Did I exit the loop because found became true? Yes, I exit the loop because found become true. That means I found it. So if I did find it, I'm supposed to return the position at which I found it. The value found at the prompt goes like this: index -1. Now why index -1? Because at the end of my if condition, I'm unconditionally incrementing the index. So even if I did find it, my index was incremented. So I actually found it one step before that. So if I did find it, index was incremented just to show where I originally found it. At my final result, I decrement the index by 1. Similarly, if this condition is not true and I exit the loop because of this part of my condition, that means I did not find it, in which case I will simply print not found. Alternately, we have another operation that may be required in an arrays, and that is known as sorting. Sorting, there is multiple, there's two algorithms that you will have to be reading, studying regarding sorting. One is the insertion sort and one is the bubble sort. Insertion sort is again paper 4. Right now we're looking at insertion of bubble sort. Bubble sort in simple terms requires a number of passes, and in that pass, after each pass, you can notice the elements are unsorted. They slowly bubble into their destined place where they should be until your entire array becomes sorted. So the worst case scenario states that if I have 7 elements in my array, if I have n elements in my array, I will require 6 passes, or sorry, n-1 passes. So 7 elements, I will require 6 passes. In each pass, I'm simply comparing 2 elements at a time. If they are in order, then I will not swap them. If they are not in order, I will swap them. So I'm just comparing 2 elements at a time. So I'm comparing 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So this is my comparison. And after each pass is completed, one element will have reached its destined position. So obviously after the first part, the largest element will have reached its destined position. So that means in the next pass, I don't have to worry about this. And I will have to focus my attention towards the rest of the array. So after the second pass, another element has reached its destined position, and my concerned array has become even smaller now. And my focus is on my remaining part of the array, because these two elements do not mean any further comparisons. They are where they're supposed to be. Same thing happens with every other pass, and after which my entire array becomes sorted. So a few things you have to remember about bubble sort. First of all, there are two types of bubble sort algorithms. There's the inefficient one and the efficient. Those both inefficient one and efficient one have many things in common. One of those things common is that they are made of two loops. One loop is the outer loop that is used for controlling the number of passes, and one is the inner loop, the nested loop, which is used for controlling the comparisons two at a time that's taking place inside within one pass. Okay, for nested loop structures, one thing to note here is that for each iteration of the outer loop, the inner loop is completely exhausted. So if for my first iteration, my inner loop will run n number of times completely. So all nested loops run this way. So let's look at the efficient loop first. Now, notice one thing, but in fact, let's do the inefficient one first. So right off the bat, I assign n with max index -1. Now, why is that so? Notice that in this loop, my loop is running from 0 to n. And say if my array size is 6, if it's 6, then I have stopped my loop at my fifth position because my n is max index -1, fifth position. Now, why is that so? That's because, let's see, in my comparisons, I'm comparing jth value to j plus 1 value. So if my counter is 0, I'm comparing the 0th value with first. If my counter is 1, I'm comparing first with second, so on and so forth. So let's just say I've got 0, 1, 2, 3, 4, 5, 6, 6 being my max index. So I stop my loop at index 5. Now, why is that so? Because I compare 0 to 1, I compare 1 to 2, I compare 2 to 3, I compare 3 to 4, and my fifth loop, I compare fifth to sixth. But if I caused it to run all the way to max index, that means there will be another loop, and I will be comparing sixth with seventh, and there is no seventh. So that's why I have to simply make my passes stop one step before so that I don't access an index position that is not part of my array, that doesn't exist. So there's no out of bound error for my out of bound index error because of this. Because if I don't do this, I'll be comparing my sixth element with the seventh element, which does not exist. So one thing to note here is this. Okay, secondly, after each pass is run, I will decrement the size of my array by 1. Now, why is this important? Well, as mentioned before, after each pass, one element has reached its destined place. So in the second pass, I don't need to be comparing this in my other comparison. So becomes an unnecessary comparison, resulting in lower execution speed. So it's inefficient programming. So I don't need to make this comparison part of my next pass. So that's why after each pass, I reduce my counter by 1 so that one element which has reached its destined position does not make it into the second pass in comparisons as well. So this is my inefficient one because it causes my number of passes to run. So for example, if I have 7 elements, my number of passes will run 6. I will always run 6 passes, no matter what. So this is the worst case scenario. If I have 7 elements, 6 passes will be at max required. The thing is, you don't always need 6 passes. You may require lesser passes than that. Why would that be the case? Well, the array is partially sorted, so I don't need that much of a sorting effort. So in which case, my algorithm should not run longer. It should not require any more passes than when the element is all my array is already sorted. In this approach, it will keep on going for this number of passes even if my array was completely sorted way before that. And this is not good programming. It's not a good approach. It requires any unnecessary number of passes in which there's nothing happening. I'm simply doing comparisons. Unnecessary comparison wastes your CPU clock cycles. Instead of this, we use the efficient algorithm. Now, apart from this outer condition, most of the code is same. Now check this outer condition. This outer condition requires a flag, and we're going to call it no more swaps. If no more swaps is equal to false, then I will keep on going. But If this no more swaps becomes true, this loop will no longer run. Now, check this out. As soon as I enter the pass, one pass, I reset my no more swap flag with true. I will start comparison inside that pass. I will compare my jth element with j plus 1. If jth is greater than j plus 1, so that means they're out of order, I will swap them. This is the technique we saw before. But the difference is that we're using arrays. I will assign the jth element temp, bring j plus 1 in j, and bring the temp value in j plus 1. Thereby, both j and j plus 1 elements are swapped. And if I did a swap, I will assign two more no more swaps flag is false. So that means there is no such thing in no more swaps right now. I may be requiring further swaps. So I do that here. When I come back up, is my no more swaps false? Yes, it is. I did some swapping. So I will go on again. I will assign no more swaps true. Now let's just say that my array has been completely sorted, in which case I will simply do comparisons here, and at no point will this condition be true because all elements are in order. None of the elements will call this condition be true. Now, if this is not true, I will never enter here, and no more swaps will never become false. In which case, after the end of the pass, my no more swaps is still true. And when I go back and check up again, this condition will become false because now my no more swaps is true, and this condition is false, and I will exit the loop. And thereby, I'm not running any more passes than I'm required. So this is a more efficient approach. If you are asked to write a bubble sort algorithm in your paper, make sure you use the efficient approach. Your focus should be on the efficient approach. Okay, now let's check out what two-dimensional arrays look like. Okay, two-dimensional arrays are basically an array that have both rows and columns. In simple terms, it's an array that has an array at each index position. That's how Python sees it. So it's an array with an array at each index position. So an array of arrays. So it's like a matrix that we see, like a table we see. The logical view of an array looks something like this. This is what a two-dimensional array looks like. It's got rows and columns, but in reality, it's just an array of arrays, right? So anyway, so when defining a two-dimensional array, we use similar syntax. We use the declare, the name of the array, it's of type array. Difference is that I will have to define two limits. The first limit defines the number of rows. So I got 1 to 5 rows. And the second limit defines the columns, 1 to 8 columns. So this array has 1 to 5 rows and 1 to 8 columns. And the type of array is integer. So it's like this one. I've got 1 to 5 rows, 1, 2, 3, 4, 5, and 8 columns, 1, 2, 3, 4, 5, 6, 7, 8, like so. So this is a two-dimensional array. Okay, if I want to access an individual elements in a two-dimensional array, of course, I will use indexing here, but the indexing changes a bit because instead of just making use of one value, I'll have to make use of two values. Those are the row number and column. So basically, I'm accessing the 4th row and 7th column. If this particular, so narrowing down to just one value requires me to mention two index positions, rows and columns. If I want to use a nested loop, if I want to if I want to access individual elements in my two-dimensional array, I will have to use a nested loop. As mentioned before, a nested loop is actually a loop that has a loop in each iteration. So basically, my outer loop runs once, and in that one iteration, the inner loop is exhausted completely. And all of iterations are run in the inner loop. So for example, for my row 0, I will run the column 0 to max column index. So it will look something like this: 0, row 0, column 0, row 0, column 1, row 0, column 2, row 0, column 3, so on and so forth. But when I've reached the max limit, say for example, the max limit is 8, my last access position will be 0, 8. After which the inner loop is finished, the outer loop will become incremented. Now I have the row value 1. So 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. The inner loop runs all over again with a new row value. So the outer loop runs once, and the inner loop runs complete. If the cycle is completed, the loop is terminated in each iteration of the outer loop. Yes. So this is a good technique to access individual elements. So for example, what we're doing here is that I'm assigning an array by the name of this table, row column mentioned here. So row 0, column 0, I'm assigning all values the zeros. Row 0, column 0, row 0, column 1, are all of them getting values 0. So row 1, column 0, row 1, column 2, row 1, column 3, all values 0, so on and so forth. So, okay. A nested loop has to have its own next statement. It has to have its own and for statement. So as you can see here, this nested loop using indentation that made it very clear that this loop is separate from this loop because the indentation says so. So for when this loop ends, I will increment this loop and this loop will be mentioned. This loop, this next is for the outer loop. This next is for the inner loop using indentation. So be sure that you mention indentations where needed because it gives you a good idea of how the inner bodies are separated from the outer bodies. Okay, similarly, if you want to print elements, the same technique applies here. The difference is that instead of taking an input and assigning some value, I'm not taking input, but I'm assigning zeros to this. If I want to simply print it, I will access the individual elements in the same technique, and this time I'm just simply printing it. Okay, this is an example of two-dimensional arrays from the past paper. We can look at that later. Anyway, moving on. Now, if you want to write some data to a text file. So why do we, by the way, need text files? Text files are stored in your hard disk, which is permanently stored. Any data that you're using currently in your program is stored in your RAM. RAM is volatile. So as soon as I turn the computer off or as soon as the program ends, the data from the RAM will be lost. You may want to save that data for later access, for later processing, but RAM, since it's volatile, will not save the data. So one good technique is that you save that data in a text file on your hard disk and you can load it later whenever it's needed, right? So important thing here is that your text file does save data in string form, by the way. So if you want to save the data in its original form, you'll have to make use of binary files. That's another thing discussed in before. But if you want to save the data in a text file, it will save it, but it will save it in string format. Each line, each line that you write in your text file is terminated by the end of line marker. So this is how my program will know whether a line, when a line has ended. So whenever I write a line in my text file, it's terminated by the end of line marker. So when I read it again, that end of line marker will be telling me where that line has ended and where another line is beginning. All of the lines that I've written in my text file come to an end with an end of file marker. So when I reach the end of file marker, it means that I've reached the end of my text file. So these two will be used when accessing data. When you want to access data, you have three modes. You have reading mode, appending mode, and writing mode. Basically, writing means that you want to write data into text file and without worrying about what was previously written in a text file. So if, say, for example, you want to write data for the first time in a text file, you can do that using write mode. Write mode erases previous contents if your text file had some contents in it. So make sure that you use write mode only when you want to create a text file from scratch. Again, use the write mode only when you want to create a text files from scratch. Second thing, if you want to write multiple lines in your text file and you're writing it for the first time, you can do it. You can write all of those lines using the write mode. So I will just mention what append mode does in a bit, but all of those lines, since you're writing it for the first time, you can write all of those lines using the write mode. Now, look at the syntax. I will open the file. This will be the file name. Obviously, it's a text file. So myfile.txt, for example, is a good example of file name. So open file. This for the mode mentioned here, I'm using write mode because I'm creating the file from scratch. It's a new file, new data. I want to write this string into this file. Now, this section doesn't necessarily have to be written in double quotes. You can assign some value to a variable and mention that variable here. In a bit, we'll be looking at some examples. So Whatever this line is written in this variable or this string will be written in this file using this command here. When I'm done writing my files, I will simply close the file so that my contents are now permanently saved in the hard disk. Okay, one thing important to note here is that if, say, for example, you write multiple lines using the write mode, and you can, once you close the file, that means the data is permanently saved. If you write data again in that file, it will erase all previous data. So if, as long as you have not closed the file, you can keep on writing multiple lines using the write mode. Once you close it, that data is saved. If you want to make any more changes to that file without affecting original data, you will have to go for the append mode. Now, append mode means that file exists and it has data in it. And I simply want to add new data to the existing data. I want to simply add it to the end of it. By the way, when you're writing data, the topmost line was the one in your text file, the topmost line was the one that was written first, and every other line comes after it. So if I want to add a line to the end of my existing text data, I can use the append mode without affecting previous data. So apart from this line, the rest of the syntax is simply same. Whatever string I want to write is mentioned here is written in this file and closed. If you want to write multiple lines, write multiple lines. But when you're done writing all of the lines, then you close the file and the data is saved. So one thing to note here is that I will go for append mode only if my previous write was concluded. My previous write was concluded with close file. If I was writing multiple lines here and I closed it, that is permanent, saved now. If I want to change into that file, I will go for append mode now. But if I'm writing data, I have yet not closed it, they're going to keep on using write mode. Okay, let's look at the read mode. Data is not changed, it's not being written, not appended. I'm simply reading the data. Okay, what I'm reading the data, I will use the file name here in this mode. One line is picked up. How do I know it's a line, just one line? Because of the underline marker. One line is picked up from the file and placed into the variable, string variable over here. And then I can use the string variable in whatever I want. I want to, print it on the screen. I want to concatenate it with something else. I want to search a substring from whatever it is. But now it's in my memory. Now it's my RAM. I can use it. And after that, close the file. You're not necessarily making any changes, but it's still a good idea to save the data, close the file. Okay, now let's look at an example of how end of file marker is used. Whenever you're required to read all lines from your text file, then you have to make sure that you've reached the end. And the end of the text file is mentioned by the end of file marker. End of file marker is simply a subroutine that when I pass the text file, it will return true if the end of file has been reached, and will return false if the end of file has not reached. So if I have not reached the end of file, I'll keep on reading. So if I have not reached the end of file, this will return false. And when I do a not on it, becomes true. If it becomes true, this while condition becomes true and I'll keep on running. Now what's happening here is that I opened a text file, test file.txt for read mode. I want 10 to read line by line. While not end of file this file, it will keep on running until it has not reached the end of file. Do what? Read a line and place it here. And what I'm doing here is I'm simply outputting the line. That's okay. And when I'm done reading all of the lines, how do I know all of lines? Because the end of file has become true. Doing a not on that will become false and I'll exit the loop. When I exit the loop, I will simply close file. So this is a good technique of how reading line by line. And you will be required to do this at various incidents where you are required to read all data from text file. If you're required to do all data from text file, you will use the end of file marker. Pass the file name to end of file. It will return a flag, true, that yes, end of file has been reached, false, end of file has not been reached. So this is just an example of how this is being applied here. I accidentally mentioned here that writing one line is write mode and remind any other lines is append mode. That's not necessary. Initially, you can write any number of lines using write mode, but if you close the file, the data is saved and you make any further changes to the that exact same file you will need now require append mode. But if you're writing the data for the first time, any amount of data can be written using a loop as long as you've not closed the file using the write mode. You don't have to use append mode separately. So please ignore this if you've seen this before. Do not worry about writing only one line, then going for append mode, writing the remaining lines. That's not necessary. You can write all the lines you want in the write mode, and append mode will only be used if you want to make changes to the text file. Okay, now we'll be discussing the abstract data types. First of all, we'll be looking at what your stacks are. Stack is basically a pile. If you add data to a stack, it was simply the stack keeps on growing upwards. So any elements that is added to the stack only is added to the top. If you want to remove some elements from the stack, it's only removed from the top. So there are two operations that can be carried on stacks. One is push, one is pop. So these are pointers that point towards the different states in the stack. My base stack pointer shows where my stack is beginning. And top of stack pointer points towards where the stack is growing. Right now, still my stack is empty. My top of stack pointer is pointing towards nothing, which is null. As soon as I add an element, my top of stack pointer will be incremented to point here. Any addition of elements will cause my top of stack pointer to move upwards. So let's just say I added 3 elements or 4 elements. My top of stack pointer is now pointing towards index position 3. If I add any more, if I push more elements to this stack, my top of stack pointer will move towards 4, then 5, then 6, then 7. And since my 7th index position is the last one, any more pushing will not be allowed because my top of stack pointer has reached the max index position. Similarly, if I pop an element, which means an element is removed from the stack, in which case after popping an element from the top my stack, my top of stack pointer will come down. So it will be decremented, pointing towards 2, another element pop pointing towards 1, another element pop pointing towards 0, and an element pop pointing towards -1. So when I reach null or -1, that means my stack is now empty. So stack operates on the last in first out concept. So any element that is on the top means that it was definitely added at the end, and when it comes time for popping those elements, the element that is on top, which is the element that was added at the last, will be the first one to be popped. Now, similarly, if you look at this queue, now queue is basically a line. Lines basically mean that first come, first serve in simple terms. So line operates on the principle of first in, first out. So any element that is start of the line is the element that leaves the line first. So right now, since my queue or my line is empty, both my front and end are basically pointing towards nothing. So as soon as I start and adding elements, my front of queue pointer will begin at here and my end of queue pointer will start increasing. Now, as you can see here, few elements were added in sequence A, B, C, D, E in the exact same order. So since A was added first, it will be the first one to leave this queue. So as stack only had 2 possible operations, push and pop, queue only has 2 possible operations, which is leave queue and add join queue. So if I want to leave a queue, only one element can leave the queue right now, and that is A. So if one A is gone, B will be the next one to leave. Now, any element that is added to my queue will come at the end of the queue. So if, say, for example, F was added to this, my end of queue pointer will point one step down to F. So my end of queue pointer is moved here. Okay, thing here is that conventionally, if you look at a queue in real life, we have a lot of people standing in a line. The person that moves out of the line in this beginning causes the entire line to move one step ahead. So if, say, for example, A was leaving the queue, my B would come into place of A, C will come into place of B, D into C, and E in the place of D. Now, this is ideally mimicking the real life situation of how a queue operates. But the thing is, this version of queue causes a lot of data movement. Every shift causes my data values to move one index position ahead. Now, considering how this is basically copy pasting data, this will cause a lot of CPU overhead. Now, to avoid this, we introduce a concept of circular queue. Now, circular queue means that instead of shifting the data around, we shift the pointers around. This way I do not have to copy paste data into all data into new places. Now this is what circular queue looks like. Instead of shifting the data, I am shifting the pointers. Let's just say that A has left the queue. So instead of moving B to A, what I do is that I shift my front of queue pointer to point a little bit down. So my front of queue pointer comes down. So let's just say A left. Now front of queue pointer came here. B left, front of queue pointer came here. Then the front pointer came here, and D left, the front pointer came here. And say E left, and the front pointer came still here. So now let's just say that meantime, after E had left, more elements started adding to the queue. So that means after E, F came here and end of queue pointer moved here. End of queue pointer moved here after another element added. End of queue point moved here, another element added. Now see, if another element, even though these places are empty, all of these places are empty, since I have reached the end of my array, my end of queue pointer cannot go further down, in which case it will have to circle back, come up here. And you will notice that my front of queue pointer is right about here, right about here. And my end of queue pointer has come reached on the top, becoming behind my front of queue pointer. It has circled back to the start to show that my front of my end has wrapped around to the start. And this is what a concept of circular queue looks like. So let's just say that after A, B, C, D, E elements left, F, G, H, I, J, K were added. And this is what happened. My front of queue pointer, A left, B left, C left, D left, E left. This is my front of queue pointer right here right now. And see, after F was added, my end of queue pointer, since after adding an element, end of queue pointer removes. After adding F, my end of queue pointer shifted here, right about the same line as front of queue pointer. After adding G, end of queue pointer moved. End of queue pointer moved for H, I, J, K, and end of queue pointer should be right about over here. Front of queue pointer is here, end of queue pointer is here. Just like this. Front of queue pointer is here, and end of queue pointer is right here. And this is the circular queue. With circular queue, my data shifting does not take place, and it causes lesser CPU overhead with copy pasting data, and I'm simply take uh, shifting around my pointers as opposed to shifting around my data. Okay. Okay, now let's discuss a third type of abstract data type, which is known as the linked list. Now, basically, linked list, again, by the way, queue, stack, and linked list, they're all just arrays. And queue and stack are simple arrays that are, working a certain way, pushing, popping, joining queue, leaving queue, based on the algorithms that support those concepts. Similarly, linked list is also an array, but the difference is that this is an array of record data. So each position, we have basically a node. As you can see here, this is one node. A node has two parts. It has the data part and the pointer part. Now, data type part is type string, pointer part is type integer. Pointer is basically pointing that what node is connected to this node. So for example, if I'm at this node, this pointer will tell me that after this node is connected. And this pointer will tell me that after this node, L node is connected. And this pointer will tell me that after this node, nothing is connected. This is known as null pointer. Start pointer is a variable that tells us which is the first node, so on and so forth like this. Okay, by the way, with the benefit of linked list is that, as mentioned before, arrays have a limitation that I cannot add elements in between, I cannot delete elements in between or at the end. Arrays are somewhat static in nature. But if I want to use the flexibility of possibly adding elements in between start and deleting so on and so forth, linked list allows us to do that. You can manipulate your array as any way you want. Okay. Now, by the way, this is the logical diagram of an array. This is what it looks like. Uh, basically, or your linked list. In reality, it's just program code. But for us to better understand what a linked list looks like, this is the diagram presented. Our linked list is an array of nodes. The array of nodes is essentially divided into two parts. One is the free nodes, which are not yet used, and one are the used nodes which have some value in it. Each element that is deleted from my used node ends up back in my free node. Free list pointer holds, yeah, free list holds all nodes that are yet to be used. And start my linked list, this is my linked list, holds nodes that have been used. My start pointer points to the first used node, and free list pointer points to the first available node for storing data. If my start pointer has a null in it, that means my linked list is empty. If my free list pointer has a null in it, that means there is no more empty space in my array to add nodes. So this basically means that there are no more free nodes left behind. So this is my free list pointer, start pointer. Okay. Now, again, it's just the same array. It's the same array that is represented, is divided into two logical parts. One is the free used linked list, and one is the free list. Okay. Now, let's look at the different operations that take place in the linked list. So this is my conventional linked list. As mentioned before, the start pointer will tell me what node is connected first. And these pointer values that we're talking about, they are simply the index positions of the nodes. So say, for example, this is node index position 0, this is index position 1, index position 2. So the start pointer is simply saying that node index position 0 is the first node. And this, since this is 1, this is 2, it's saying that node my 0th node, let me it's like this. Yeah, let's say this is my 0th node, this is my first and my second. Start pointer says 0. Why? Because it's pointing towards the 0th node. 0th node is first node. In 0th node, the pointer value has 1 in it. So it says that what that means is that 0th node is pointing towards 1 as the first next node. The first node is pointing towards 2 as its next available node, and the second node is pointing towards nothing because it's ending here. This is my last one. Now let's just say I want to add a node at the beginning of my link. Say, for example, my existing letters are B, D, and N. I want to maintain alphabetical order, and I have a new node that has value A. A is smaller than B, D, N, so it begins with it belongs at the start. This new node that I just used, it has the index position 3. Index position 3. So since it has to belong at the start, what I can do here is that I adjust my start pointer. My start pointer is currently pointing to 0. I copy that 0 and place it here, so that my new node, which is now going to be start node, will point towards the 0th as the second node. And I update my start pointer to have value 3 in it, telling everybody that now this third node will be the first node in this linked list. And that third node will use 0 to follow this node, and everything else will be the same as before. So that's one way of using linked list to add an element at the start. Similarly, if I want to add an element at the end, I will simply do this. Say, for example, I wanted to add this third node, this node number 3 right here with value P. It belongs at the end because it's P is greater than all of the connected letters. What I can do is simply update the last node pointer. It previously had null in it. I will simply place 3 in it now, so that this last node is pointing towards this node, and this node is pointing towards nothing because it is the last node. I will assign null to it. If I want to delete the first node, this is deletion. How can we do that? Simply update the value. So for example, right now, my start pointer is pointing towards 0 as the first node. What we can do is that we can update the start pointer with the value 1, thereby telling everyone that now 1 is my first node. And this 0 will no longer be part of the memory. My start pointer tells us the start node, and start node is now the 1, node number 1, thereby excluding 0, the 0th node from my linked list altogether. Similarly, if you want to delete a node from the end, simply what we do that, we go to the second last node and give the pointer value null, telling everybody that there's no node after this node, thereby ignoring this one from my linked list. If I want to add somewhere in between, so for example, I have node number 3 here having C. As you can see here, C belongs between B and D. What we do is that we copy the value in this pointer right here and paste it here. So originally this pointer was having 1 in it, pointing towards node number 1. But now I will copy that value here so that this node points towards this node. And I will copy this node's value here, allowing this node to point towards node number 3, making this linked chain, allowing this node to be in between this and this, thereby adding a node in between. Similarly, if I want to delete a node from in between, what I can do is that I copy this value here and paste it here, allowing this pointer to directly point, this node to directly point towards this node, and thereby eliminating this node in between. So this is how your linked lists work. Again, these are the two-dimensional arrays that represent how these workings show. For example, as you can see here, start pointer points towards one, telling us that my first node, this is my first node with B here. First node is my by this is my first node. And this node is followed by node number 2, which has D in it. And this node is followed by node number 0, which has L in it. And L node has pointer in it, pointer minus one or null in it, thereby telling us that there is no node after this. By the way, if you're using 0 index, null is represented by -1. If you're using 1 index as your first index position, 0 will be your null value. Similarly, you can see here, I just added a value, I added A to it, and A is supposed to be at the start. So my start pointer is updated. Start pointer is now telling us that start is, by the way, is 1 is crossed out, and start pointer is pointing towards node number 3. So I'm beginning with A. Now my originally first node, which is node number 1, has become node number 2, my second node. So that's why A is now pointing towards, A is at the beginning, is index position 3, node 3 is the beginning, is pointing towards this node, and this node is followed by D, and D is followed by L, and L is not followed by anything. And this is how you add elements and how your same operations take place, but you see the two-dimensional array version is also very easy to use.